Good afternoon, ladies and gentlemen. Welcome to our SESAR Digital Academy webinar. Our topic today is smarter, safer, and more efficient arrivals. My name is Olivia Nunes. I am an ATM expert at the SESAR Joint Undertaking, and I am very pleased to be hosting this session today. Our aim is to provide an opportunity for everybody to learn about what's going on in SESAR firsthand from the people that are working on the projects today. And before getting into the topic, I would like to share a bit of information on how the session will work. Let me share my slides. Okay, first of all, I want to say that we had so much material for our session today that we decided to split it into sessions. So if you want to save the date, we're going to have a part 2 of this webinar on the 21st of October. And stay tuned. We host webinars regularly, and they can all be found in this page later on YouTube for playback. For the program, it's on the SESAR JU webpage on the events. Then for those of you that maybe are not so familiar with the Livestorm tool, we aim at making this very interactive. You're welcome to use both the questions and the chat. Please, if there are questions, actually things for us to read, put them in the questions, because the chat gets a lot of messages and we cannot guarantee that we will see the questions there. So the questions will be answered, some of them live by the speakers during the panel that we will have. And all the questions that are not answered at that time will be answered later in writing. Also, some of the questions will be answered live, not speaking, but writing. Our speakers can type. And not only our speakers, but they have also some people in their teams that will be typing as well. So you will see either the speaker or one of us or someone that's supporting the speaker typing the questions. The Q&A file will be shared afterwards together with the playback of the webinar so everybody can see. And without further ado, I think we can get into the topic. We have 3 speakers today, and so our first speaker, if you want to come into the stage, please, Sean.
Hello.
Welcome, Sean.
Thank you. Hi, Olivia. Hello, everybody.
So Sean has around 10 years of experience working for NATS on SESAR projects. So she was here in SESAR 1, as was I actually. So we've worked together for a long time. And prior to that, she trained as a controller in the London Area Control Center. She is currently the Deputy Project Coordinator and Technical Lead in the Enhanced Arrivals and Departures Project, so PJ01, for those of you familiar with the SESAR jargon. And she is leading a solution which is focusing on optimized climbs and descents. And she actually also manages another project, which is also a SESAR project. It's a VLD, a very large demonstration, VLD3, for those that are familiar with the jargon. And she is managing the NATS contribution to this project. Today, she is going to be talking to us about the work that NATS is doing on arrival management streaming for optimized use of systemized airspace. Sean, the floor is yours.
Thank you, Olivia. So good afternoon, everybody. Today, as Olivia said, I'd like to talk about the work we're doing in SESAR to investigate support to the descent phase of flight through arrival management streaming. The project's overarching aim is to improve environmental efficiency for arriving aircraft. Together with our linked third party, Frequentis Orthogon, NATS are developing a streaming AMAN prototype to provide longitudinal spacing of aircraft through the airspace with the aim of transferring delay out of the holding stacks into the more fuel-efficient phases of flight, sequencing and streaming aircraft arriving into the London terminal manoeuvring area so that aircraft can fly using the systemized airspace structure using performance-based navigation routes with optimal descents from the top of descent, minimizing the need for tactical radar vectors and step descents. The ambition is for arrivals to continue to be managed for optimal runway throughput, with fuel savings through reduced time spent in the holding stacks and less constrained descents, whilst using a systemised route structure. So first, a little bit of background about our current X-Man operations. Both Heathrow and Gatwick have arrival management systems which use a 550 nautical mile data horizon. When delay is predicted to be greater than or equal to 7 minutes, then at the 350 nautical mile speed reduction horizon, our X-Man partners, who consist of MUAC, DSNA, Shannon and Prestwick, will slow down aircraft by up to Mach 0.04. When delay is predicted to be greater than or equal to 5 minutes prior to the descent, the NATS controllers will also apply a 250 knot descent speed. Between these two measures, stack holding for a slowed down flight can be reduced by about 90 seconds. So for a medium vortex category flight, this saves about 50 kilograms of fuel. In this SESAR project, we're now looking into how to improve arrival management even further to achieve more efficiencies and debunch aircraft arriving into the airspace at the same time. Under the current X-Man, controllers in NATS and our partner ANSPs, as we've just seen, apply a uniform speed reduction when a delay is predicted. So although this takes some time out of the holding stacks, it doesn't solve the problem of aircraft arriving in a bunch, as they would still have the same speed reduction applied. So a bunch of aircraft just turns up slightly later, but still close together. Working with Frequentis Orthogon, NATS are looking to develop the AMAN so that, as well as absorbing delay, aircraft can be longitudinally separated prior to top of descent before they enter the systemised airspace structure. With this streaming AMAN, rather than just passing a blanket speed reduction in cases where there's predicted delay, the aim is for aircraft which may not have sufficient longitudinal spacing for separation along a route to be assigned a time over a metering fix, or TOM, in order to facilitate a more steady stream of aircraft for the controllers to be able to apply optimised descent operations in the systemised route structure. This time over metering fix will also allow for some delay absorption, but there may be a trade-off to achieve the desired spacing and facilitate continuous descents. So we can see in the diagram, as aircraft pass over the data horizon, AMAN starts its calculations. As they cross the 350 nautical mile horizon, in place of a blanket speed reduction where there's delay, a time over metering fix is issued to each of the aircraft, and the aircraft fly to this time by the time assigned points. Now, looking a bit closer in, as you can see in this diagram, the streaming AMAN not only assigns target times to the pre-descent waypoints, but also to the mid-descent merge points and to the initial approach fixes. These time over metering fixes to the mid-descent merge points and initial approach fixes will be translated into descent speeds to be passed by the controllers as proposed speed instructions. In our current operations, controllers have to manage any such interactions through these merge points with tactical radar vectoring. With streaming through the merge points and to the initial approach fixes, aircraft will be able to fly optimised descents along the systemised airspace structure with little or no need for radar vectors or stepped descents. This concept is expected to provide benefits not only in periods of high demand, but also when traffic levels are lower, as bunching will still occur in these circumstances. There should no longer be a need to maintain a buffer of as much as 7 minutes of holding delay, but due to more precise information, time over metering fixes can be provided even when minimal delay is expected, whilst ensuring that the pressure on the runway is maintained. So although some individual aircraft at the head of a bunch may not slow down as much in the cruise as they would with the current X-Man procedures, it's expected that more aircraft overall will have some delay absorption applied, resulting in a further reduction to stack holding in addition to the gains from current X-Man operations. So on this slide, I'd just like to illustrate what I've been talking about. On the right, we can see our target airfield, so Heathrow, and on the left, there are 3 aircraft currently under the control of our partner ANSPs. In this example, the 3 aircraft are each predicted by the A-man to arrive at the pre-descent merge point at around about the same time. So a time over metering fix will be applied to each of the aircraft. The pilots will fly to this time, meaning that they will arrive at this point separated by around 90 seconds each. That 90 seconds is a configurable amount within the A-man though. Therefore, they can go through the descent nicely streamed. The A-man provides further speed refinement advice, which can be passed by the controller to ensure that they maintain positive separation over the aircraft and can also ensure that any aircraft joining manage to join merged with these aircraft. It is expected that there'll still be some holding required. It won't eliminate the need for this completely. We're hopeful that if the concept is successful, we'll be able to roll out the operation, not just to airfields with existing A-man, but to those that may not have an A-man at all. And now for a further illustration, I've got a couple of videos to show you. So in this first video, we're going to see what happens when no action is taken. The white diamonds represent the points that A-man predicts the aircraft will be with no action taken. And there's a 2-minute lead vector shown on each flight. So as you can see, some of the aircraft arrived nicely streamed. Others, I've just paused it, others, as we can see here, arrive closely together, which makes optimized descents very difficult without using radar vectoring. So in our next video, we're going to see what happens when A-man takes some action. So again, the white diamonds represent the point where the aircraft will be with where A-man predicts the aircraft will be with no action taken. And now we have a blue cone illustrated. And the point of the blue cone is where A-man wants the aircraft to arrive through those points. So again, as we see, we have some bunches of aircraft approaching, and I'll pause again just to point out. Between here we have a Speedbird and a Scandinavian very close together. However, with the action of A-man, it brings the Speedbird forward slightly, so speeds up slightly, and the Scandinavian stays in around the same place, slightly further back, so that they're nicely streamed. In this example up to the north, we have another Speedbird and a Finnair. And in this case, the A-man is slowing the Finnair down very slightly to this point, and the Speedbird is being slowed down further so that it has a neat spacing behind it. And we can see that as the aircraft go through the descent, they're nicely spaced out. With the aircraft coming on the screen now, we can also see how some delay absorption is applied. So I'll pause again just to show this example of the Qatari here. There's no immediate aircraft around it, which means that spacing would be required. However, the A-man is sending the Qatari a little bit further back so that some more delay is taken in the cruise and descent phases of flight rather than being spent in the holding stacks. So now I'd just like to talk about the work that we've done so far and the work that we're still planning on doing. In 2020, we ran a recorded data trial. We used 2019 traffic data to ensure we had busy enough samples. One of the main outcomes from this work revealed that the current trajectory source, which is used by A-man, wasn't sufficiently accurate for the purposes of streaming. The current A-man uses ETFMS data from the network manager, but this was never created to provide the accuracy that this concept needs. So use of ADS-B and Mode-S speed for greater trajectory prediction is now being investigated. We're also doing some further work on how to manage flights which take off from within the A-man horizon. For example, a flight from Amsterdam to Heathrow will have less flying time to achieve a particular time over metering fix, and it may not need to be streamed through the same initial point as a long-haul flight, as it wouldn't be at those higher cruising levels. For example, a flight from Singapore approaching the pre-top of descent point at flight level 380 wouldn't interact at this point with an Amsterdam flight, which may only be cruising at a maximum of flight level 240. These flights would only interact towards the next merge point. And we've started conversations with our ANSP neighbours and airspace users, as this isn't a concept that we can make work by ourselves. Currently, neighbouring ATSUs pass speed reductions to aircraft for the X-Man operations. This concept means that they will be passing time over metering fixes instead, but potentially to more flights than they pass the X-Man instructions to today. In the future, we may look into passing the message through IOP, or the electronic flight bag. Looking ahead to our upcoming exercises to further mature and develop the concept, we're planning a simulation activity in our ACE simulator to test the industrial prototype, which will be run towards the end of this year. This will be supplemented with controller workshops and a limited human-in-the-loop real-time simulation. Investigative work's also taking place into the use of ADS-B data in a live non-operational demonstration of AMAN trajectory prediction capability, and this is planned for early 2022. With the development of this streaming AMAN, we aim to manage arriving aircraft and our airspace in the most efficient manner in order to enable fuel savings, taking a portion of delay in the cruise rather than the stacks, spacing aircraft ready for the descent, and enabling better descent profiles from cruise levels whilst flying on closed-loop trajectories as part of the systemised route structure. To achieve this aim will ultimately be a collaborative effort across European partners and airlines, working together to achieve the vision of a single European sky in order to maximise environmental efficiencies to the greatest extent possible. Thank you for your attention.
Thank you very much, Sean. Thank you for the very informative presentation. I think actually it was the first time I see the whole animation. I think it made it much clearer. Thank you. And so we'll talk to you later. Feel free now to stay on stage or step off stage. And I want to welcome on stage now Anaïs Lacroix from SkyGuide. Anaïs?
Yes, good afternoon, everyone. Hi, Olivia.
Welcome, Anaïs. So let me introduce you first. So Anaïs is an engineer in telecommunications from Lyon, and she specialized at ENAC with a master in cooperative avionics. And then she entered SkyGuide in 2008 in Geneva. And she was first in ATFM, air traffic flow and capacity management, and then in operations development projects and validation activities, so CPDLC, stripless system. And she has been in R&D projects with SESAR for a long time as well. So I've worked with Anaïs for a long time. And she's now back in ATFM for capacity studies, as well as daily business like traffic forecasting, sectorization, optimization studies. And so she combines actually this more operations today projects with R&D, which is, I think, great for us because she gets the first experience of the ops as well. She's currently involved in Project 7 and in Project 9. That's jargon, I guess, for some people. So just to say, this is the UDPP, Project 7, so the involvement of the airspace users. And Project 9 is network, so dynamic airspace sectorization and integration into demand capacity balancing. But she's here today to talk to us about a project that's already closed and in operations. That's the Zurich streaming processes for the early morning long-haul arrivals. This was started as a series of SESAR demonstrations, and my understanding is now in operations, and Anaïs will tell us all about it.
Okay. Thank you, Olivia, for the introduction, and good afternoon, everyone. So, do you see, Olivia, do you see the screen? All good? Okay.
Perfect, thank you.
Okay. So I will introduce you to the SESAR project we had in Zurich regarding the arrivals streaming. what happens in Zurich, the context of this airport, is that we have a night curfew, and the first landing is allowed at 6:04 in the morning. And during the first arrival, during the first hour after the opening, we have a majority of long-haul flights incoming, with a lot of connecting passengers to European destinations. So what happens is that everyone, of course, wants to be first, and the prevailing ATC concept of first come, first served has the drawback of queuing the aircraft at the star's entries, resulting in holding and vectoring patterns, and therefore unnecessary fuel consumption and CO2 emissions in these early morning arrivals. So actually, we don't have any capacity constraint at that time, but we observe inefficient paths, and that's what we want to tackle with the SESAR projects. So here, as shown by the extract of this slot coordination attribution, is that we don't have a capacity problem at this early morning time. But Zurich is a hub airport with important variation in the traffic demand during the day. So we have wave of inbound flights followed by waves of outbound, creating a cycle of peaks and gaps during the day. And to accommodate these peaks, we need to focus on the arrival waves, considering the impact on the following outbound waves. So some example of the situation that was needed to be improved before. As illustrated on the left, we had a flight that was highlighted in red that was not planned in the sequence, but had to fly at 360 to get in. And on the right, we had a flight which came very too early, because 10 minutes before the opening of the airport, and he had to fly at holding and caused all the following flights to be vectored. So that's what we wanted to tackle. So of course we have an AMAN system and an arrival management system at Zurich since 20 years now, the frequency orthogon as well, but it only tackles the flights which are present in the TMA. So we needed to complete with procedure to upstream this arrival flow management. So we decided since many years, since 2010 approximately, together with Swiss and Zurich Airport, to really closely coordinate to streamline these early arrivals. So in 2014, the Green Wave project was created only for the Swiss long-haul flights between in the time frame of the first half hour, so until 6:30. So what we observed is a very good adherence to the target time provided by the pilots, and the flights will arrive in the TMA already sequenced. So that's why we wanted to increase the benefits of this procedure. And that's why eStream was launched afterwards by extending the time frame to 1 hour, so until 7 o'clock local time, involving all the airlines present in this time frame, and adding a strategic phase in order to target as well the flight planning process. So really from the beginning, when the airspace operation, the airspace user operations fill the operational flight plans. And afterwards, in 2018, the PG25, so also known as eStream, was launched, which tackled the enhancement of this eStream procedure by involving the network manager and using this the new network manager B2B service called API for arrival planning information. So eStream, the objective of this procedure was to establish an early approach sequence to prevent holding and any ATC delay. How? By assigning a target time of arrivals, so target time actually at the star entry fix at Zurich, to hold long-haul flights in this hour, which would reduce the CO2 and NOx emissions of this flow. And as well, another aspect that we wanted to add in this project is to provide flexibility to the airline's operations by giving them the possibility to exchange target times between the aircraft in the arrival sequence. So what we wanted to achieve is, of course, at least the same benefits and increase the benefits of what we observed during the Green Wave project, which were 75% decrease in the time spent in holdings, and the savings in the CO2 emissions amounted until 1,800 tons a year. So Stream was a completely new process for for all the airlines that were involved. So that's why we invited them. We invited their agents at Zurich Airport to explain them about the process and communicate about this new project. And actually, the collaboration of these airlines was really key and necessary for the success of this new procedure. Stream has two phases, so a strategic one and a tactical one. The strategic phase consists on the provision of a strategical arrival sequence on the day before the operations. So it's a sequence based only on the arrival slot at Zurich Airport. This is for the Airspace User Operational Center to take into account these target times to fill their operational flight plans, and for them afterwards to coordinate their departure at the outbound stations. The tactical phase consists of the provision of an updated arrival sequence 5 hours prior to landing, based on the estimates directly received from the flights. Another key point of this procedure was that the ATC was not impacted. The procedure for the controllers did not change. There was no new procedure for them, and the ATC principle, first come, first served, prevailed. So the SESAR trials took place from June 2015 until June 2016. And afterwards, the Stream procedure became mandatory for all the inbound flights, from 6 till 7 o'clock in the morning, local time. And the IAP was published since October 2016. So the strategic phase, as we said, is really to support the process at an early stage. It's to target the flight planning and enable lower cost index flights, because this sequence provide strategic expected target landing time with a 10 minutes window time frame for their adaptations. So this expected landing time and the possible range for adaptation to the cruising speed should already be considered in this flight planning phase, because this improves the efficiency of the overall process. From the start, everybody is aware of what they have to expect and what range of action the flights can have. So this strategic phase is sent out each day at 11 local time for the day after. Then the tactical phase, so it's on the day of operation. And once all the long-haul flights are airborne and have reached their top of climb, they are sending to their operational center their revised and accurate estimated time of arrivals at Zurich based on their actual takeoff time and their flight time. Afterwards, the operational center sent back transfer these estimates to SkyGuide, and SkyGuide retrieves all these estimates from the flights. And in case we don't receive the estimates directly from the airlines, we take the times from the NM system, so from the ATFMS flight profile. We compute the arrival sequence, and we send back this sequence with the ordering to all the operational center involved, and which then transferred back to the flight crews, their TTOs. And then the crews manage their flight to manage their TTA at Zurich. So how look like this tactical sequence? So it's as it is, it's sent each day at 1 o'clock 40 maximum local time, and it considers spacing of 2 minutes for each flight. So the SESAR trials have showed a significant reduction in tracks time and tracks distance in the Zurich TMA, and as well a significant reduction of the number of too early arrivals, and therefore a reduction of the holdings. However, from the Stream trials, some recommendations were highlighted. First, being that the NM estimates for the long hauls are not accurate. So the ones that were taken from the ETFMS profile, because the trials demonstrated that these estimates diverge from the actual flown flight profiles and are not accurate enough to be reliable for the arrival sequence. It's because that the long haul flights at that time, they are not yet in the ECAC area, so the NM system haven't received the position report yet directly from the aircraft. So it relies only on the flight plan, and the trial showed that the TTOs were not achievable by the crews if we take them from this the ATFMS profile. Another recommendation which came out of eStream is also we have a majority of long-haul flights during this first hour. We still have 2 or 3 short-haul flights, and we need to integrate them to have a whole flow considerations. And for that, we needed to integrate the network manager into the process. And that that's where came from the PG25, also known as Xstream, which was a very large-scale demonstration. So we had 3 different exercises within this project, and one of them was directly a follow-up of the eStream project and targeting the enhancement of this eStream procedure by involving the network manager and using this new B2B service, the arrival planning information, enabling the ANSP to send a target time of arrivals to the network manager. So the objective of PG25 was still the same: provide efficient and sustainable early wave arrival at Zurich Airport, still by involving all the airlines in the targeted time frame, still to provide a flexibility for the airspace user to be able to exchange or to swap flights between their aircraft in the sequence. And the new specificity was to use the new B2B API service from the network manager. So how it was working: so once the stream sequence was computed, all this sequence and the target times was sent to the network manager. So the target time over for the long hauls did update the ATFMS profile for them, which then improved the accuracy of their of the long haul flight profile in the system. And for the short haul, we embedded them in a cherry picking regulation, and we transferred the target time over for them, which resulted in NM to assign them a CTOT, so a calculated takeoff time slot for them, compatible with their target time at Zurich. And this regulation was aiming to improve the adherence of the short-haul flights within the sequence and to avoid them popping up in the established long-haul sequence and disturb the already established one. So we published an amended IAP for that. We informed all the airspace user. And still, another important point is that the procedure was still transparent to the air traffic controllers. So what was new in this process? So still we have the strategic phase with Zurich Airport based on the arrival slots. We receive on the day of operation all the estimates directly from the flight crews. We compute the sequence. It was transferred to the network manager thanks to the API. Then the network manager assigns the CTOT slots for the short-haul flights. And then the sequence is sent back again to the airspace user and then to the flight crews. So what resulted into from this PD25 trials that, of course, creating cherry picking regulation creates delay, generates delay. So in 1 month of trial, we have generated 66 minutes of delay. Also, the majority of the flights had a 0-minute delay. So 72% of flights have had only enforced their scheduled takeoff. And as well, we have minimized the difference between the ETO and TTO when providing the target time for the long hauls. And this showed that we could improve the ETFMS flight profile for the long haul flights which were still outside the ECAC area. So what was achieved is that we have an early established sequence. We have optimized flight profiles and, of course, optimized the landing spacing. They arrive at the approach sector already sequenced. So as conclusion from this PG25, we optimized the operation thanks to an improved collaboration between all the stakeholders. So directly from the gate-to-gate planning, but from as well the flight planning phase until the touchdown. And therefore we optimize the fuel burn and therefore CO2 emissions per flight. We optimize the landing sequence with a more efficient use of the available capacity. And we optimize the airspace user operation, providing them improved hub operation and passenger connections. The other, on the ATFM aspect, there was no added ATC workload. the procedure is totally transparent to controllers, and the benefit and the work is really upstream. And we could see as well that the generated delay supported the predictability of the shortfalls in the sequence. So we see here that the ATFM regulation aspect is not only providing a smoothing of the traffic, but also it enables the flights to be pushed closer to their scheduled arrival time. So this project enables us to go towards performant and sustainable environmental operations. The benefits are for all, airspace user, ATC, and the airport. We improve the flow prediction and the TMA and the terminal sectors, thanks to a better anticipation and a more efficient coordination between all of us. The improvements led to higher punctuality and on-time performance, taking some volatility and some buffer times away from the systems. The ATC work was facilitated. We made better usage of the available capacity. We reduced the tactical intervention. And as we cherry-pick shorter flights to streamline the whole flow, maybe we can talk about a green ATC delay, because we saw that delays are created, but with environmental benefits. Here we saw that regulations are not only for capacity-constrained situation, but they show as well their potentiality to smooth out the peaks and gaps in the demand, and it's a useful mechanism to push the flight closer to their scheduled time. So maybe in the future we can consider and apprehend the regulation and the delay not only as a means to resolve a safely capacity-constrained situation, but as well as a means for the NSP to allow green and environmental flows. PG25 also provided improvements in terms of environmental sustainability of air traffic by reducing the holdings, the vectorings, reducing the fuel consumption, CO2 and noise emissions, and reducing the aircraft noise impact and improving the air quality is and will remain a priority in the vicinity of airports. And this as well, all this reduction, fuel consumption, CO2, noise, it's aligned with the aviation objective to reach the net zero greenhouse gas emissions by 2050, as set by the European Green Deal. And at last but not least, the flexibility for the airline operation, because we need as well a collaborative framework, which as well consider the airspace user business needs within this ATFM planning. So allowing the airspace user to customize and optimize their flight to maximize the passenger connections and airlines operations is to be considered for the future. So that's why we are now working with the Swiss and Zurich airport towards this TTA concept for the future. So thank you for that, and we will see us after for the questions, I think.
Thank you very much, Anais. You do have a few questions there waiting for you on the chat that you could, of course, you couldn't see. No, sorry, not on the chat, on the questions tab. And so feel free to stay on stage or step out. I'll call you all later at the end. Now we are going on to our third and last presentation today. And can I ask Frank to step on stage, please?
Hello, everybody. Hope you can hear me.
We can hear you right. Thank you. So Dr. Frank Holzapfel, sorry about that. Thank you. So Frank is a senior scientist at the German Airspace Center, DLR, Institute for Physics of the Atmosphere. So he graduated as a mechanical engineer at the University of Karlsruhe, and then he specialized in measurement and modeling of turbulent swirling flows at the Engler-Bunte Division of Combustion Technology in Karlsruhe as well. And that is where he got his PhD. And it's after the PhD that he joined DLR as a research scientist. That was, I think, in the late 90s. And that's where he still works, but he's now promoted to a senior scientist. His research concentrates on wake vortex, and that's what he will be talking to us about today. So it includes large eddy simulation, fast time, wake vortex model development, field experiments, wake vortex advisory system, risk analysis, and wake vortex decay enhancement, which is our theme today. And he's also a lecturer at the University of Munich for fluid dynamics, or at least he was in 2007, 2009, and I don't know if you still do that. And that's all as an introduction. Frank, you can talk. The floor is yours.
Thanks a lot, Olivia, for your kind introduction. Ladies and gentlemen, I want to warmly welcome you to my presentation entitled Mitigating Wake Turbulence Risk Doing Final Approach via Plate Lines. But first of all, I would like to thank Olivia and her team for this great opportunity to share our achievements on wake turbulence risk mitigating devices with this great audience of experts. So as an introduction, I would like to share a video which is showing the numerical simulation of the A340 aircraft in high lift configuration doing final approach and landing on a runway equipped with a series of plates that you see on the upper left, which we call a plate line. In this animation, the velocities are color-coded, high velocities in red, intermediate yellow, low velocities in white. And as you can see in a few seconds, the high velocities in the area where the vortex cores are will first reduce over these plates, and then disturbances will propagate to both sides with the effect that all along the stretch where a following aircraft might land, the vortices would be less strong than as they would be without those plates. Now I have to continue with my talk, which should be here.
Yeah, that's correct.
So, why plate lines? As many of you may be aware, wake vortices pose a potential risk to follower aircraft, and that's why in the 70s, minimum separation distances were introduced after the introduction of the B747 aircraft that limit the capacity of big and busy airports. But maybe only few of you may be aware that the highest risk to encounter wake vortices prevails in ground proximity. So with the plates, we want to widen the bottleneck posed by this flight phase in terms of wake vortex risk and capacity. So doing flight at higher altitudes, the wake vortices induce each other a descent speed such that they would descend below the flight path of a following aircraft. This, of course, is not the case close to the ground. This situation is shown here with these 4 photos on the right, where we see a numerical simulation of the vortices in an end view with a V crosswind from the left. So when these vortices approach the ground, they will first diverge, but they produce a vorticity layer close at the ground, which will detach at a certain time, rotate around the primary vortices, which leads to some vortex rebound, and then interact with these vortices, which leads to its decay. So you might see that this happens slower for the love vortex on the left time, which is because the crosswind shear will attenuate the production of the secondary vorticity. But what is more important is that this upwind vortex really hovers in the area where a following aircraft might land. And this leads to the statistics that you see on the left below. These are pilot reports of wake vortex encounters collected during the years 2000 to 2000, from 2000 to 2004 by NUTS. So it's essentially London Heathrow traffic. And you can immediately see that the highest risk to encounter wake vortices prevails for inbound traffic in left, in the lowest height range extending from the ground up to 500 feet above ground. Now let's talk about the concept of the plate lines. As you can see in the photo right below, taken at our experiment that took place at Vienna Airport, the plate line consists of several upright plates which are installed underneath a glide path. We think this is a passive, economic, robust, and safe method to accelerate wake vortex decay. The physical mechanism hiding behind that is shown on the upper left. So once the wake vortex approaches the ground, it will induce the secondary vorticity. but at the plates, it will much more rapid induce a so-called omega-shaped secondary vortex, which will actively approach the primary vortex. It is then wrapped around the primary vortex, and both the spiral-shaped rings induce themselves a propagation speed to the left and the right, which will cause premature wake vortex decay. So what are the benefits? We will have accelerated wake vortex decay, of course, less wake encounters leading to less go-around, so in general, some increased safety level. The next bullet point needs a little bit more of an explanation. So we think the plates may also help to compensate increased encounter risks brought along by runway capacity enhancing methods, like for example, the Recut EU pairwise separations. So what's Recut EU? Recut EU is the separation scheme that follows the ICAO scheme, which consisted of 4 categories based on maximum takeoff weight, by a 6-category scheme, which considers the strength of the produced vortex and the vulnerability of the following aircraft. This is Recut EU phase 1. Phase 2 is pairwise separations, and there individual aircraft types of the leading and follower aircraft are considered. Recut EU is designed such that the strongest and most severe encounters that could occur with ICAO separations will not occur. But on the other hand, less severe and non-critical encounters might occur or will occur at a higher frequency, and the estimate is like 60% increased. So it's easy to assume that, for example, pilot associations or airlines might not enjoy to see that encounters, although they are benign, would be more frequent. And our latest results, really very fresh, showed if you would combine these two methods, Recut EU pairwise separations and plate lines, you will most likely be able to reduce these encounter rates below those of Recut EU, which is already operational for several years at several European airports. So the next bullet point will lead further into the future. There we talk about potential capacity gains that could be achieved by dynamic pairwise separation distances. So again, the term pairwise, which refers to individual leading and individual follower aircraft, but dynamic means that on top of that, we also consider wake vortex behavior as controlled by the meteorological conditions. The simplest example would be a crosswind that would transport the wake vortices out of the flight corridor. So again, for Vienna Airport, we conducted some study with a dynamic pairwise wake vortex advisory system developed by DLR. And there we found that in 85% of the cases, the reduced separations are limited by wake vortex evolution. Again, you may guess it, close to the ground. So the combination of such an advisory system for dynamic pairwise separations with plate lines might be an opportunity to make available even more capacity in a safe way in the longer term future. So this is a survey of the scientific work that has been done since the idea of the plate lines came up in the year 2008. So we started with towing tank experiments showing on the upper right. In such a towing tank, a simplified aircraft model is towed through a water channel, and the vortices are visualized with dye. At these 2 blue arrows that you hopefully see, we have placed obstacles at the ground of the towing tank. And if you watch clearly, you can see that from these obstacles, disturbances propagate along the vortices that lead to accelerated wake vortex decay. We also conducted a real high number of high-end computational fluid dynamics simulations. Example is this final approach where you see now vorticity detaching from all parts of the aircraft, like flap ends or slats or wingtips. And there we investigated, for example, the impact of turbulence, of headwind on crosswind, but we also optimized the plate dimension, their height and their separation for aircraft of different sizes. Finally, in the year 2013, we conducted flight experiments with the DLR research aircraft Halo, which you see in the lowermost video, where the vortices are visualized with fog and smoke. And if you can discriminate the people which are seen there, you see that already a relative small aircraft like our Gulfstream aircraft produces impressive vortices. So it's easy to imagine that vortices produced by large aircraft are really a potential risk for follower aircraft. The outcome of this experiment was that the lifetime of the longest lived and so potentially most hazardous vortices could be reduced by 1/3. Now we come to our Vienna measurement campaign that we conducted in the framework of the SGU project PJO2 Earth in the time frame from May to November 2019. On the right, you see an aerial view of the field below the threshold of runway 16 and at a distance of 400 meters directly behind the localizer, a first blade line consisting of 8 blades with a height of 4.5 meters and a length of 9 meters and separated by 20 meters. Another blade is installed at a distance of 340 meters to this first blade. We had available 3 Leosphere lidars to measure the vortices, which were alternatingly placed in the lidar positions L1 through L5. So we sometimes measured over the plates or between the plates or between the plates and the runway. With these lidars, we captured about 30,000 wake vortex evolutions, from which we could use about 600 with and 600 without plates to conduct an analysis, from which I want to show you a few selected results now. So to give you an idea how these measurement results look at first hand, you see on the left such measurements. On the top, vortex transport. You see vertical position above lateral position of the vortices. The vortices with plates are in green and blue dots, while the vortices over flat ground are red and in magenta color. And you see that we focus on a safety corridor with an extension of plus minus 50 meters from the extended runway center line, because vortices attracted out of that corridor couldn't harm following aircraft. If you look at the plot below, which shows vortex decay in terms of circulation decay, you see a substantial scatter of data, which is on one hand due to the fact that we have here aircraft of very different sizes from the A320 to the A380. But it's also obvious that we have to find other methods to clearly see the effects of the plate lines. And one example of that is shown here on the right, where you see so-called probability density distributions of wake vortex lifetime for different ranges of vortex strengths, of circulation strengths. So the curves with plates down are orange, those with plates up are in blue. And you see while the vortices are strong, these distributions are more or less identical. But with progressing vortex decay, they deviate more and more from each other. And in the lowest circulation range, the average lifetime of the vortices is reduced by the plates from 100 to 70 seconds. Here a few more impressions from our Vienna measurement campaign. On the upper left, from the time where we installed the plates. So it's also important to understand that these plates were temporary. They had to be removed after the campaign. Next, a photo from the SESAR Visitors Day. Then again, the A380 over the plates that you saw before, and an end view of a landing aircraft during dusk. Here I show you 4 selected key results. The first one would be that the lifetime reduction potential achieved with the plates is about similar to that occurs in a high turbulence regime. For this, it's important to understand that turbulence really accelerates vortex decay such that wake encounters would be very rare. So we achieve qualitatively something similar like that. We also found that a single plate line is almost as effective as 2 lines. So when we are going for permanent installation of the plates, we will install only a single plate, which would typically be situated directly in front of the localizer. Then we found that lifetime reductions increase with aircraft size, from 22% for an A320 to 37% for bigger aircraft like a B777. Finally, we found a 50% circulation reduction for heavy aircraft, assuming a 120-second separation to following medium-type aircraft. As I mentioned before, the Vienna campaign used a temporary plate design, but of course we've been working also on a technical plate design for permanent deployment at an airport. And here the challenging criteria are really, on one hand, the stability. The plates have to withstand wake vortices, but they also have to withstand real strong storm. But at the same time, they have to follow the frangibility requirements set forth by ICAO. So we did that quite systematically by developing 15 potential plate designs that you're seeing on the top, which differ in the number of mass or the material covering the plates, which could be truck tarpaulin or honeycomb panels. There are also solutions where the tarpaulin would be moved down in case of strong storms, or where the blade would bend to the side to withstand stronger winds, driven by some spring extender mechanism, or with flexible plates, window shutter solutions, blades stabilized by ropes, and our green solution, Tuya hedges. So a number of experts helped us to define these criteria that you see on the lower left and to give them weights, which finally helped to develop a ranking of these potential designs. And there we first selected these 4 most promising solutions circled in yellow and conducted detailed stress analysis with finite element methods as shown on the lower right. And the result of this selection process with the help of the experts is shown here. This plate would consist of 4 frangible aluminum masts covered by 9 honeycomb composite panels. Currently, we are on a phase to get approval from Austrian authorities for the installation of a plate line or a plate prototype at Vienna Airport. Then we also had a look at the separation reduction potential compared to RICAD EU and RICAD EU pairwise, also by applying this method. So what does RICAD EU do to really define their separations? They are considering so-called reasonable worst case situations where the vortices would remain in the flight path and live very long. With that, they define a reasonable worst case decay curve, which is shown here in red on the left, which in fact corresponds to the top 2% of the longest lived vortices measured at London Heathrow Airport out of more than 100,000 tracks. So we did something similar with our Vienna measurements and ended up with this black solid line, which agrees well with the RICAD EU curve. If we do the same procedure with plates, we end up with a dashed line, some accelerated wake vortex decay, which can then be translated in the plot shown on the right, where you see the time gain of potentially reduced aircraft separations depending on the vortex age. It increases with vortex age. And the black line shows the curve for this traffic mix that you also should see on the left, while these colored curves correspond to aircraft of different size. And as you can see, with increasing aircraft size, this separation reduction potential increases. Now, these curves can be translated into the RICAD EU schemes. On the left, RICAD EU, which consists of these 6 aircraft categories, from the super heavy, which is essentially the A380, down to light aircraft. And if we have a look at one example, for example, a leading upper heavy category aircraft followed by a lower heavy category C aircraft, there we would find that the 4 nautical mile separation of RICAD EU could be decreased by half a nautical mile, corresponding to 12.5%. If we look at these percentages, we see they are quite smoothly distributed and range between 12 and 15%. If we do the same with pairwise separations, and for this we considered pairings of 62 different aircraft types, we end up with quite similar and slightly better results. Again, the distribution is mostly very smooth and averages to a separation reduction potential of 15%. This brings me already to the conclusions and an outlook. So I hope I could convince you that we're doing here some smart exploitation of vortex dynamics, enabling the passive, cost-effective, robust, and safe blade line method. An installation of blade lines reduces wake vortex lifetime in between, depending on the aircraft size, from 22 to 37%, bringing along improved safety levels, resilience, and fuel efficiency by avoiding go-arounds. The separation reduction potential for recut EU or recut EU pairwise separation schemes varies between 12 and 24%, but is mainly around 15%. We think a near-term goal could be to install blades together with the introduction of recut EU pairwise separations to compensate for encounter risks brought along with such solutions, and possibly with other solutions that are aiming at increasing runway capacity, like reduced runway occupancy time or reduced minimum radar separations and time-based separations. We're hoping that not too far in the future, we will be able to install a permanent blade line, possibly at Vienna Airport, and then we would conduct dedicated wake vortex measurements again to enable in the longer term future these dynamic pairwise separations. And then more generally speaking, this approach would help for more efficient use of airport capacity, which contributes to climate and environment-friendly aviation by avoiding delays and holding patterns, and it also may postpone building new runways. And this brings me to the last slide for those who are interested to dig a little deeper, which gives the survey on references, journal publications, also links to the SESAR EU projects in which we were active, and it lists 2 awards where we at least were finalists or ranked second place. And that's it from my side, and I'm looking forward to your questions.
Thank you very much, Frank, for your very nice presentation. Now, you do have a few questions, but Grigori has been answering some of them. And we're going to address some of them as well at the panel. So maybe if I can ask the other 2 presenters, Sean and Anais, to join us on the stage. Hello, welcome back, Sean.
Hi, thank you.
Hello, Anais.
Hi.
Okay, so well, we had many questions. Many have been answered already, but I would like to go back to some of the themes, starting with Sean. There have been a lot of questions asking, well, what are these? Are these compulsory times? Will you pass the time to the aircraft? What is this best endeavor? How will you monitor? Will they comply? Will they not comply? Is this the CTA? Another flavor of the CTA? So if you can elaborate a little bit on this.
Yeah, of course. So I suppose first of all, it's important to say these are not necessarily compulsory, hence the reference to best endeavours. So what we're trying to do is the AMAN takes on board all the information about the arriving aircraft, and it proposes a sequence. But we do understand that it may be that not every aircraft is able to be streamed for whatever reason. It may be a reason within the cockpit. It may be a reason within the partner ANSPs who aren't able to apply that target time for any such reason. So we are very much saying it's following the principle of our X-MAN operations at the moment, which is also a best endeavours. So when there is delay predicted, we ask our partners to apply that speed reduction in X-MAN, and it's the same sort of principle. We would be asking the partners to pass the time over metering fix to aircraft on the understanding that it wouldn't always be possible. It would be really fantastic if we could, as in my diagram, I suppose, have every aircraft completely streamed through our systemized airspace. But certainly for a first iteration, this isn't particularly likely. So we're looking to minimize interactions and ensure that we can have the most optimized descents possible through our airspace by just minimizing those interactions whenever possible. In terms of whether it's actually a controlled time of arrival, again, no, it's not specifically a CTA, a controlled time of arrival, because this implies effectively a non-deviating status where controllers can't actually do something to an aircraft, and we don't want to take that away from controllers. They still need to be able to apply active control. They may need to for example, vector aircraft even in the cruise, or apply different speed instructions as necessary. So none of what we're proposing is to take away that control, but it is just to provide those improvements. And we think even if this is just done for a portion of aircraft, it should still provide some improvements.
All right, thank you. So can I just dig a little bit more? What's the difference nowadays? An AMAN will produce a time to lose, time to gain advisory for the en route controller, and they will say, well, I need this aircraft to lose 3 minutes, and then the controller will manage. Is this actually just these 3 minutes that would be presented, and then the en route controller has the kind of the choice? If they can, they pass it on to the aircraft, but if they can't really afford to give this aircraft like kind of self-management, then they would try to manage it with speed, or not manage it at all if they can't. Would that be the idea?
Yeah, so I would say it's very open at the moment. So we are still quite in the early stages of this concept, and it may be that different ANSP partners would have different preferences to how they actually manage this, whether they do pass on the time over metering fix, or whether they pass time to lose, time to gain instead to the aircraft. So we're not closing the book on any of these options. What we are doing within the work in Project 1, Project 37 work, is we are looking into the concept. We're trying to measure how it could be on a very basic understanding of how to actually implement it, but all the time we're coming up with perhaps more questions than answers, which makes for really interesting work, and we hope that as we go through we can start answering those questions. But quite often there isn't a single answer to a question, and we're very much keeping the floor open to possibilities.
Okay, excellent, thank you. So I'll now move on to Anais. Also on the same theme of times, and if you like, a target time to a metering fix, even though you don't call it TOM, essentially I would say we can consider it's kind of similar. And so we have had a lot of questions about, well, how many times is this updated? Like, how many times do you give to the aircraft? Because in this case, in your case, for these long hauls, you definitely pass on this time to the aircraft. And when do you freeze it, let's say?
So actually, there is no update. Once the sequence is sent to the airlines at 1:40 local time in the morning, this sequence is frozen. So there is no update afterwards, no revision to this arrival sequence. So the airlines can update their estimates up to 1 o'clock in the morning, and at 1:40 the sequence is frozen and sent back to everyone.
All right. So there is like the pre-departure. It's like there are like 2 checkpoints. Let's say one is pre-departure, and then there's the one at 1:40 when everyone is already airborne. Would that be correct?
At 1:40, all the long haul are airborne already, but not yet the short haul. So the NM will attribute the slots once they get their activation of the flights afterwards. Yeah, just that.
And we've had a lot of questions also about the short hauls, and actually I'll get back to you, Sean, on that. But since now building on this with Anais, can you explain a little bit more then what happens? Because you had calculated all this at 1:40 when, the people that were flying these short hauls were potentially still in bed, and then they get up and they get on the aircraft. And then what do you do when they pop up? What's exactly the situation?
So actually they are provided a seat like they are regulated, like if there were a capacity problem in Zurich, they receive a slot. So for majority of the flights,
you have previewed some gaps in there for them, because you already know there will be so many.
Exactly. We have 2 minute caps for each of the flights during the arrival sequence, even for the short hauls. And then to enforce them to stick to this planned slot in this arrival sequence, we attribute them acetate. Well, NM, the network manager, attributes acetate compatible with their target time at Zurich, so that we can rely on their popping up at the time we want, actually, in the planned sequence.
All right. And what is this zero delay CTOT that you had? Because many of them got a CTOT that was exactly the same time that they were scheduled.
Exactly.
How would you define or explain the benefit of me getting a CTOT that's my same time, let's say, that I was planning on departing?
That's really to ensure the departure depart on their scheduled time. So because normally with a normal slot we have a -5 +10 window to depart, but this slot reduces this window, and this we can enforce the flights. We can increase their adherence to the departure time and therefore to the arrival time.
Okay, and how is this understood? You would say, or people kind of, space users are not used to these non-delaying CTOTs and are kind of thinking this is a mistake or is not understood?
No. Actually, this CTOT or this regulation part was only part of the PG25 trial, and as it was, of course, generated a bit of delay, and delay is attributed to the INSP. It's of course difficult to keep it on operations. So it was only for the trial, and but for the future we have to think. We have to think of different attribution of this delay, because in the end it's a benefit for everyone. But it was only for the trial, and this part of the system of the procedure for the short haul is not in operations. So yes, now we stick to the adherence of the short hauls by communicating with them and yes, keeping closely them in the loop.
I understand. Okay, thank you very much for the explanation. So I'll now move on to you, Frank. We had a lot of questions. Gregory was answering some of them about what are these plate lines, all these designs that you had, and some look like hedges, and would they really be able to stand crosswinds? And how would that, was that really difficult to find a design? And another question we had, which I thought was interesting, is, well, if they can't stand, wake vortexes, could you foresee potentially doing something like that on the site so you could, protect from crosswinds the runway, or would that be unfeasible?
Okay. Thanks for the several questions. So the winds that the plates have to withstand are clearly defined. They are from a norm, which is called Eurocode, and which considers the wind situation at different places. So for Vienna, in our case, and would consider like something like the 1 century storm. And there it's clearly prescribed how stable the plates have to be, and we used finite element computations to see whether the plates could withstand that. This is, of course, not simple. We had to develop mechanisms which I couldn't describe in detail, which at the same time make sure that the plates are frangible in case an aircraft would miss the runway and run into those. But we were able to meet these competing interests. And now we're in the phase to get the approval from authorities. And for that, we will also get external advice. And we went through the same procedure already for our temporary plate lines. So we know how that works a little bit, and we're confident that we would get that. So with the side winds, that's an interesting question, which I didn't give a thought so far. I'm not so sure. Of course, basically you can also protect from winds, but typically if you have an obstacle in a wind, you also produce turbulence. And these plates would end somewhere. There you would produce vortices. So I rather know about problems, for example, with runways bounded by a forest canopy. And this would probably rather bring additional problems. I don't think that would be really a very excellent idea, but one might give more thoughts of it. I don't know.
Excellent, thank you. So, and I would like now to go back to Sean about the short hauls. I think I had warned you. Yes, because we had many questions, both for the Sky Guide long hauls, but also in a way what you're doing is also a long haul, because you're talking of over 500 miles, and I mean it's not 4 hours, but it is very long. So, and here we're not talking of a few aircraft because it's in the middle of the day. What do you do with these short hauls that pop up from all over the place when you have already got your target times? Do you change those target times over the metering fixes, or are they frozen, or do you like leave gaps already in advance?
So yeah, this is a really difficult problem, and it's one of the things coming from our recorded data trial that kind of flagged up as an issue that needed to be addressed. So we're looking into it further. We're actually, as you say, it is quite a long haul, looking out beyond 550 miles for the data horizon, and then within that we've got our kind of more short hauls, which perhaps take off within that horizon, but are still reach high cruise levels. And then we've got our regional flights, which are much lower as well. So we started thinking in terms of these three categories of flight and how we manage them. Ideally, I suppose this concept is to support a systemized route structure, and the ideal would be that we would have a different route for such shorter haul and regional flights to fly their own route and not interact with the long haul flights. Once a time over metering fix has been sent to the aircraft, that is then frozen and it won't be changed. You could potentially go changing a lot and it could cause problems. So that's not something that's going to happen. So there's the potential to look at increasing the spacing within the horizon for kind of slotting in the in horizon departures. And one thing to bear in mind as well, I suppose, is that we are still maintaining, of course, a reservoir of aircraft in the hold to ensure that we keep pressure on the runway. We can't afford to have gaps in landing. So that gives us some leeway, of course. It's not as efficient, but initially we're looking for more efficiency than we have today. We're not necessarily just aiming for perfection with this, because that would be very difficult. So where we can, we will aim to include those in horizon departures in the sequence. We might also look at, instead of the configured time that I gave in the example of 90 seconds between certain points, then between nearer in points, we might look at trying to achieve 60 seconds, for example. One other factor, of course, is as well as incorporating these aircraft into the sequence, is that they don't have as much time to achieve a particular time to lose or time to gain as they would have if they had an extra 300 miles of flying. If they've only got 100 miles of flying, it's harder to achieve more of a change to their profile.
Okay, thank you very much. So I'll now that you were saying about the aircraft that do have a long time to achieve, then that actually leads me to ask Anais again about her presentation about the long hauls. How much time, let's say, what's the spread of the amount of time that you can actually modify reasonably so that the aircraft will actually slow down for in this update that you do at 1 hour 40? So how can you give them like 15 minutes and they will really absorb that? Does that depend on whether they come from the east and or the west? Is there more flexibility, let's say, on one side or the other, or north or south?
No, there's no distinction between the origin of the flights. Actually, the system computes the target time based on the estimate, and with a limit of 5 minutes difference from the estimated receive. So we can give a target time up to 5 minutes difference, minus or plus, from the estimated receive. So it can be achievable by the flights, because they have 4 hours of flying, so they cannot reach or lose 15 minutes in the flight. So we give them 5 minutes to the limit. And if we can't compute a reasonable sequence by providing all the target times by 5 minutes limit of their estimate received by the companies, the airlines, then we cancel the sequence, because there we consider it's not achievable for the flight, and we cannot ask them to do that.
All right. Understood. So now there's a question for both of you in turn. and before moving on to Frank, is that we had a few questions about, isn't this a scheduling problem? So the problem is in the first place that we have too many flights scheduled to arrive at the same time. And then maybe we should fix that rather than then on the day come and start modifying the schedule times. How would you reply to that? What's your view, your take on this?
So if you want me to go first, I'd say, yeah, if we can improve schedule times, that sounds like a really good thing to do. It's not particularly within the scope of our project, but maybe there's some significant improvements to be done there. Within the work that we do, though, we effectively, as I've said, we have a reservoir of aircraft in the holding stacks to ensure that we never kind of run dry for the runway effectively. So where we have such capacity constrained runways as Heathrow, we need to make sure that we always have aircraft ready to land on the runway. So in effect, there's always that level of inefficiency of needing some holding. What happens at the moment is that the aircraft arrive and spend quite a bit of time in the hold. And what we're proposing to do here is, when we know that there will be that holding, to remove some of that into the more fuel efficient phases of flight. So the aircraft will still land at the same time as they would have without this concept in place, but they will be flying in a more fuel efficient manner for that time overall.
Thank you. That makes sense. And then how about you, Anais? With that,
Yes.
I think you mentioned that actually you did not have a capacity problem at the first thing in the morning.
Indeed, that's why we don't have a capacity problem. So really the aim to provide this strategic sequence the day before the operation is really to enhance the awareness of the airlines about their STA at Zurich, and to plan efficiently. So they consider this STA at Zurich and not plan to arrive 10 minutes earlier, which would result them to hold at Zurich airport before the opening of the airport. So it's really a matter of awareness and communication of this STA at the airport, and for them to plan consequently. But yes, we don't have any capacity problem at that time. So yeah, we still have.
So that's in the end why the short hauls were not implemented, because you wouldn't want to have CTOs when you don't really have a capacity problem. Would that be?
Totally. Yeah.
Okay. So now I'll move on to Frank, who's promising to give you some more capacity in where needed. And so we had some questions to say, wow, this increase of capacity is always welcome. When? What's left for this? How far are we from actually being able to reduce this separation dynamically between aircraft and based on these plates? And is that dynamic, or can you also just do it statically, let's say? So if you can elaborate a little bit on what's the next steps, let's say, to reach that point.
Yeah, the next step I see, which really could be done relatively near future, is the combination of the plate lines with Ricard pairwise separations. As I was explaining in my talk, this Ricard separations, pairwise separation, the second stage, will already bring along more capacity, but at the expense of higher encounter rates, which are not severe. And if we put the plates there at the same time, these encounter rates could be substantially reduced. So I think we could have both in the end by installing the plates and introducing Ricard pairwise separations, capacity increase and safety increase at the same time. And in the longer term, when this would be static, it depends just on the aircraft pairing. In the longer term, we could go to dynamic separations, where we consider the meteorological conditions, which is not so easy because they would change in time very quickly. And even measure them in the moment is not so clear, but they have a strong impact on wake vortex evolution. And we have developed a wake vortex advisory system for dynamic pairwise separations, which we already demonstrated also at Frankfurt and Munich Airport, and it worked quite well there. So this is something for a few years ahead, but we think there is a way also to bring along even more capacity at good safety levels. But a near-term goal could be this Ricard pairwise separations with plates, And within the SESAR project, the plates have already achieved a sufficient maturity level, TRL 7, which proves that the safety benefits are there. So they are more or less proved and could be very soon be used to the benefit of FreeCAD EU pairwise.
Okay, so just to be clear, for the you reduce the wake, you accelerate the wake decay, let's say, and that if applied with a normal RICAD EU, decreases the the encounters that may happen for having potentially aircraft a little bit closer, that or even with the pairwise, with whatever scheme you have, it just will produce fewer encounters than you would have today.
Yeah.
And then for reducing, it always has to be dynamic. It always is dependent on the, for actually reducing the separation, let's say below the current RICAD EU or pairwise.
Okay.
That always has to be dependent on the weather. It's not possible just based on the plate lines and say, because I have plate lines in my airport, instead of 5 miles, I think you showed around 0.4 miles below. So I can do between these two aircraft instead of 3.6. That's always dependent on the weather.
That's true. I mean, in my talk, I showed a reduction potential even for RICAD EU and RICAD EU pairwise separations, but that possibly couldn't be used because we also have to consider the whole flight path where we don't change anything with the plates. And the whole flight path would be secured by this wake vortex advisory system that considers it. So if we have situations with a little crosswind or turbulence or stable stratification, all that would reduce wake vortex lifetime. But then this crosswind typically at the ground is lower. And I also showed that the vortices close to the ground also move against the crosswind with a certain speed. For that, that's why the bottlenecks would still be close to the ground, and here the plates could really help.
Okay, so another question we had is how long. So if you envision what you need for, you have the weather conditions, let's say, that allow you to reduce the separation. How long does this last for? Is it like changing every 10 seconds, every minute, every hour? I think it's a little bit like we have with time-based separation that's based on the headwind. So how would that work? How do you envision that?
Yeah, that's of course very important question for real operations, and we investigated that for the measurement and demonstration campaign we conducted at Frankfurt Airport, and I don't recall the exact number, but it was something a little longer than an hour average duration of reduced separations. And there the requirement was that we would have to predict that at least 20 minutes in advance.
All right, so now you would get like a new separation. Still, it's always with one of these tools that tells the controller for every aircraft. That's like for the time-based.
Yeah. You of course have to have tools, but what I would like to add, there were also situations where you could have reduced separations for a whole day. We found that also in our study at Vienna Airport. I mean, there are days where the wind is just strong, and then you have a certain component perpendicular to the glide path, and then that's easy. Then the vortices are just blown away.
Okay, but that's actually when you have crosswinds, which has other issues as well. So usually the ideal runway doesn't have a crosswind, let's say, so to speak.
Yeah, but crosswinds of 2 meters per second are already enough for wake vortices, and that's not yet a risk for aircraft or problem.
Understood. Well, thank you very much. I'm afraid we're reaching the end of the time. So I just left to say thank you very much to our speakers. Thank you very much, everybody, for being here. We have a poll here.